computer. Okay, so this is session 2 with examples of algorithmic interview questions. And today you will see some very famous interview questions. The first is two-sum, three-sum. So you see it's 11 questions today. Two-sum problem and similar three-sum problem. So given an array of integers, find two numbers such that they add up to a specific target number. Okay, so this is the function two-sum. It should return indexes of those numbers in the order, first the smallest one, then the largest one. Indexes should be not zero-based, so it should be 1, 2, 3, and so on. And assume that each input have exactly one solution. Okay. And here's the solution. We already had it analyzed by Alex Nee on one of the previous seminars. And the approach is very simple. We go through the numbers. And as we go through the numbers, we check if we already have seen this number before. So we create a dictionary called seen. And if not that we've seen the number so that together they add to the total which we need, which is target. So we check if target minus number, which we're looking at now, is in seen, then we're done, right? We have number in the seen dictionary and the current number. So we just need to take the indexes and return. And you see seen, target minus num, and position. So the dictionary seen, the key is the number, and value is position of this number. So it's a very simple solution. It's linear, so it's a big O of n, where n is number of elements. Beautiful, right? Well, this is a three-sum problem. Well, it's a similar idea, but if you write it without iter tools, it will be quite convoluted. So I decided to write a solution which using iter tools, and iter tools module has a function which gives all the combinations. Okay, so this is two-sum, three-sum problem. Let's look at another problem, very famous problem, Towers of Hanoi. So the idea is you have disks of different sizes, and they form a tower so that smallest is on the top. And as you move disks around, you always need to put bigger disks under the smaller disks. So they always should be in order like this. So the task is to move the whole pyramid to another pole. You can use intermediate one to help you. So the game Towers of Hanoi uses 3 rods and a set of disks stacked on the first rod and the largest disk on the bottom, thus forming conical tower, right? The aim of the game is to move the tower of disks from one rod to another. Only one disk can be moved at a time. We can only take the topmost disk, cannot take disk from the middle, and the disk cannot be placed on top of a smaller disk. Okay, so here is the solution, and the solution is recursive. Well, this part is just to output the steps as we go, and each step consists of 3 actions. And you see this function Hanoi, and it calls itself recursively. Okay, and I actually encourage you to copy this text and run it in Python to see the output and to see how it works. And the reason why I wanted to see the counter is because the number of steps grows very fast as you increase number of disks. Okay, so you see that Hanoi for n is recursively derived from Hanoi of n-1, and n-1 will be recursively from n-2 and so on. Okay, so this is a famous problem. And next one, oh, this one I love. I remember trying to solve it myself, and the problem is like what we need to do. We need to find the largest rectangle which fits under the histogram, right? So usual solution is you start from the left, and you try like, for example, here you start and you have like this, right? Then you go another step, and it will be either this or you can take this one, right? Then another step, and you try to see all kind of different rectangles which can fit, and eventually you need to select the largest one. So how you do it? As you go, you can create different stacks, and there are solutions including 2 stacks and 1 stack. So here is the solution, and it's a little bit tricky how to actually do it. I don't know how people give this type of problem on the interview. I was not able to do it on like, well, I was not giving it on the interview, but when I tried to solve it in real time, I couldn't. It takes like precision with the indexes and stacks, and again, so this is the solution. And again, I don't want to go through it like in too much detail, but let's just read. So we create an empty stack, right? So this is the stack, and it is just a list, right? Then for every hist of I, so this is hist 0, hist 1, hist 2, these are bins of our histogram, changes from 0 to n minus 1. We do the following: 0, same, or going up, right? 0, same, or going up. If stack is empty or hist is the same or higher than the bar, then push index to stack. Going down, so this is, for example, going here. If this bar is smaller than the top of the stack, then keep removing the top of the stack while top of the stack is greater. While doing this, we'll try rectangles as following. And then in the end, if the stack is not empty, then one by one, remove all the bars from the stack and do the step B, is going down for every removed bar. And this actually can be achieved by a simple trick appending -1 to the histogram at the very beginning. And this way we will avoid adding a piece of code to do this ending operation. So this is the implemented code. And again, we don't have enough time to go like in detail for what it's doing, but I recommend you, well, first try to do it yourself and see, like, suppose you have 20 minutes and try to write a solution yourself, maybe without looking at, just after I reviewed kind of how it's done, try, like, let me know if you succeed. Reverse linked list. Again, very famous problem. So we have a linked list, which is a set of nodes where each node has a value and points to next node, right? And we need to reverse it. And there are 2 solutions. One solution creates another list, and another reverses list in place. So this was quite interesting how we go through the list and reverse all the pointers. So we start at the beginning of the list, right? And then what we're doing, so current is the head of the list. So this is where we are, right? Then, well, head is a variable, right? Which is passed here. It's the first object. It's the head of the list. Then we change the head to the next element of the list, right? And then we go to this next element and we set it to previous. and then previous is current, and we continue. Okay, I should have put like some sort of picture and diagram to show exactly what's going on here. But basically, you have a list going from head in direction, and then for each element you repoint and rename, and then continue moving as you do it. It's actually simple, yeah, but I needed to put a picture. Anyway, and here we just create a separate list, and again, you can follow the code. Binary heap, very important structure. So binary heap, maybe max heap or min heap, is a data structure which looks like a binary tree, where each parent is greater or smaller for min heap than values of children. So this is the only rule of how you build the heap. Binary heaps are a common way to implementing priority queues. Okay, the heap is usually stored in an array. So the top of the heap is element number 0, its children elements 1 and 2. Next, children are on the like 3, 4, 5, 6. So under 1, we will have 3 and 4, and under 2, we will have 5 and 6, and so on. So our pyramid is stored as a linear array, and if we start with array, which where elements are in any order, you can heapify it to place this in order so that the largest element will be what 0, and then will be children, and so on. And this is the procedure how you do it. Basically, what you do, you go through the elements and you swap them. And so this is a heapify procedure which does the swapping, and this is the procedure to build the whole heap. So you see for each element, so we go through the list, and if needed, we swap elements, we heapify them. Okay, time complexity of building heap is linear. If we're adding an element to the heap, it usually happens at the bottom. So think about building a queue. Like, for example, patients are coming to the hospital and they're at the end of the queue, but then based on the priority, they can percolate to the top of the queue, right? So it's a priority queue. So you add them to the bottom, and then you take them from the queue always on the top, right? And okay, so this is about heap. Okay, next problem, contiguous array. Given an array having only ones and zeros, maybe pretty big array, many elements, find max length of contiguous subarray with equal number of zeros at once. So for example, if we have a small area of 0, 1, 0, there are two solutions. One is 0, 1, and another is 1, 0. So how many solutions? 2. So that's the number we need to return. So the idea of solving this problem is beautiful. The idea is we change zeros to minus ones. Then as we go through array and calculate the running sum and store it in the hash. So every time we meet 0, actually minus 1, we go down. Every time we go 1, we go up. And contiguous array means that beginning and the end of array are on the same level, right? So we store in the hash key is the sum and the value first index when we got the sum value. If we hit the same value again, if it is already in the hash, this means that we had equal number of ones and minus 1 between these points, so we can calculate the length and update the max length as needed, and then eventually return it. So complexity is linear. It's a beautiful solution. It's a beautiful idea to substitute 0 to minus 1, right? So this is actual implementation, and you see it's very short. Okay. Next problem, longest consecutive sequence. Given an unsorted array of integers, find the length of the longest consecutive elements sequence. It should be run in linear complexity. So example, we have these numbers, and the longest consecutive sequence will be 1, 2, 3, 4, right? So the output should be 4. Idea, make a set of all values. If value is in the set, but value x minus 1 is not, then x may be only the beginning of the sequence, right? Then follow the sequence, check if x plus 1 in the set, and so on. So you start with making a set, and then you go through the set. And this is actual implementation. And again, it's very simple, very elegant. Max subarray. So this is a Wikipedia page about this problem. This is actually quite beautiful. My son received this exact problem on Google interview, and he solved it with the help of the interviewer, and he ended up getting into Google, so it's good. Okay, explanation of this algorithm. For a list of numbers, A0, A1, A2, and so on, for each index, we can look at all possible series starting from 0 to I minus 1, ending with I, and select the biggest sum among them. So let's call it SI, sum ending at I. We will calculate those numbers for all i's and select the maximum among them. And this will be the answer. Okay. So again, given array of numbers, find the continuous subarray with the largest sum. So the subarray can start at the beginning, but it may start not at the beginning, right? So it can start somewhere, end somewhere, and we calculate the sum of elements between them, and we need to find the maximum. Okay, here's how we do it. So if I equals 0, there is only one series, A0, so the sum is A0. If I equal 1, we have A0 and A1, and we have A1. And by the way, A's, the elements may be positive and negative. So we need to find the maximum. So S1, which is the series with the maximum value, will be a maximum of A0 plus A1 and A1, which is, but A0 is actually maximum of, it is S0. So we can rewrite it as S0 plus A1 or A1. Okay, so remember this, because you will see how this will continue. For 2, we have 3 series, 3 different sums. A0 plus A1 plus A2, A1 plus A2, and simply A2. But then if we look on the first 2 elements, we can rewrite it. I have to, okay, do it later. We can rewrite it like this, plus A2, right? Because A2 is added to both of them, or as S1 plus A2. Okay, so S2 equal maximum of S1 plus A2 or A2, and so on, so on. So that's okay. Maybe I went a little bit too fast through it, but again, I encourage you to go a little bit slower for yourself. So here is the how we get to the maximum, and this will be the answer. And so you see the algorithm goes linearly using these formulas and prints the output. So the complexity is big O of n. I think this simplification is quite like for me, it took me some time to understand. Oh, really? It's true? Yeah, it's true, and it works for positive and negative numbers. Okay, it's a beautiful problem. Okay, next one. concatenate words. Given a list of words without duplicates, return all words which are concatenations of shorter words in the same list, right? Time complexity, where n is number of words and l length of words. So for example, if we have input cat, man, cats, dog, cat, cats, dog, man, woman, cats, dog, and we need to return words which are concatenations of shorter. And the answer is cat, cat's dog, and cat's dog, right? And so this is the solution. We go through the words and we test if the word is concatenation, and we append it to the result, which is then can be printed, right? And how we do the test? Well, we use the dictionary, which is created here, empty dictionary, and it's passed every time into the function. And so we maintain things which we already tested before. So it's a kind of idea of dynamic programming. So if the word is already in the dictionary, we return it. If whatever, we will not go, you can go like slowly through the code. It's quite trivial, but just for demonstration how this kind of problem can be solved. Okay, next one, jumping kangaroos. Two kangaroos start jumping from positions x1 and x2. They jump synchronously and in the same direction, but the length of jumps may differ. Question, will they meet at the same location? Okay, they start jumping from different positions. So one start jumping from here, they move in the same direction. And if this jump is bigger than this jump, then eventually maybe they will meet, or maybe the big jump will jump over the slower kangaroo and they will never meet. So we need to find if they will meet or not. Okay, so this is the solution. We move in the same direction, we divide, and we check if we end up in the same place or not. Okay, again, it's a kind of trivial solution. We're just dividing to see if they will meet or not. Okay, so complexity is constant, right? And final tax bracket. Again, this is very, very simple. Problems like this, they give you an interviews just to see if you can do a for loop. We have incremental income tax brackets, calculate total tax for a given income. So these are tax brackets for like less than $10,000, you charged this amount of tax, and then between 10,000 and 20,000, you charged this, and then this, and then this, and so if you have more, then you split like in these periods, and you'll be charged this and this and this, and like for the rest, you'll be charged the remainder. And here it goes through these tax brackets and calculate the total. Okay, so this was the last problem for today. And it took me about half an hour to go through this. Let me stop recording.